Hey, this is a video for 4.7, Solar Radiation and Earth's Seasons. So go ahead and check out the overview and set up your guided notes. So the Earth makes its journey around the Sun in an elliptical orbit, and there are two things that are going to indicate temperature and seasonal changes on the planet. For one, we have a revolution, and that is determining the year. So one full journey around the sun is the equivalent of 1 year. It's actually 365 and a quarter days. That's why we have to have a leap year. Now, responsible for our day from sunrise, sunset, but for 24 hours, it takes that long for the Earth to spin on its axis. So these are the two things, the two factors that we are really looking at. But there's one other one. The tilt of the Earth is responsible for our seasons. So the reason we have a fall and a summer and a spring and a winter and is really having to do with the solar energy or the insolation. That's another term for solar energy, the insolation that's hitting the planet. So this represents the Earth on its axis. This represents the summer sun. Now it's northern hemisphere summer sun, but in the summer on the June solstice, it's going to hit the Tropic of Cancer, and it's going to give the most direct rays to the northern hemisphere. Now in December, on the winter solstice, it's going to hit the Tropic of Capricorn in the southern hemisphere and give the most direct rays there. So it is the northern hemisphere's winter because we are not getting the direct rays. Now what does this look like in more detail? Well, one thing first, the day's length, the length of the day, is going to increase the radiation intensity. So if we have a longer day, in other words, the longer amount of daylight, we're going to have more intensity from the radiation. That's why we have more solar intensity in the summer, because our days are longer, the time between sunrise and sunset. Now, insolation versus latitude. So at higher latitudes, again, latitude is how far away from the equator you are found. So if we look at us in New York, we are going to have more of the insolation. In other words, more of the solar energy is going to be absorbed by the atmosphere. So at higher latitudes, it's a lot more difficult to warm the surface of the planet. When you're getting more direct rays, you go through less of the atmosphere, which means less radiation is going to be absorbed by atmospheric particles. And then finally, at higher latitudes, we're also spreading that insolation over a larger area. So they're not only indirect rays, but they're also spread over a larger area. One thing you can do is take a ball, like a basketball or something, a balloon even, turn the lights down and shine a light on it. If you shine a light directly on it, it represents this. If you shine a light at an angle, you'll see that that light is spread out, much like I've shown you in this diagram. Now we have this phenomenon called albedo. And albedo is literally the measure of a surface's reflectivity. Like that. Okay? We have, for example, ice has a very high albedo. It is very close to 1. So most of that will be reflected. It will reflect this solar insolation. It will reflect the solar rays. Some very small amount will be absorbed by the ice. Now, oceans have a very low albedo. Okay, it's closer to 0. High albedo is closer to 1, low albedo closer to 0. So oceans are actually among the darkest surfaces on the Earth, even though this is drawn blue. If you look at a satellite image of the Earth, the oceans look very dark, almost like a navy blue color. So in the oceans, a very small amount of it will be reflected. Most of this insolation will be absorbed. So this red represents how much infrared radiation or solar insolation is absorbed. And this will be causing temperature increase because it will be absorbing the heat. Now the scale of an albedo, so we have environmental And we have, for the environmental, we have the open ocean, which is a 0.06. It's almost zero. Soil is 0.2. The sea ice is 0.6. Ice, that's literally ice on top of the ocean. And then snow on top of ice is the closest to 1.0. Now, for anthropogenic or man-made causes or sources, we have asphalt, which is like pavement. The dark asphalt is on the roads. 0.1, it's very low. Concrete, which is like cement. Concrete's 0.4. Whoops. And that's it. I mean, there's other surfaces, that are probably going to reflect more, like certain roofs that are painted a certain color. But these are just basic albedo numbers. Now, these can all contribute to the urban heat island effect. And what is that? Well, the urban heat island is when a metropolitan area absorbs so much solar insolation that it has a higher temperature than the area around it. So areas like this have low albedo because they will be absorbing the solar energy. And they have a low albedo because of maybe dark roofs, asphalt, and concrete. These are all man-made surfaces. This is impacting the hydrology because you may have faster evaporation, but also it's increasing the costs of cooling because of the air conditioning. So again, an urban heat island like New York City is among the worst heat islands in the world. We also have Newark, which is out in New Jersey, also a very, very warm heat island as well. What I would like you to do is respond to this check for understanding. And finally, I would like you to practice by describing the solar intensity across northern latitudes during winter. I hope that this video was informative. I thank you for your attention, and I will see you soon.